No, no, no. No, I'm perfectly thank you. Thank you. It's a pleasure to be here. See, my name precedes me. Okay, I want to give a series of lectures, 3 lectures on that really complement what you heard from Andrea on the design of micromachines and materials. All right, and I'll sort of tell you a little bit about the motivating ideas behind each of these. When I'm talking about microscopic machines, I really want to think about what it would take to miniaturize the kinds of things that we build at the macro scale and try to implement them at the microscopic scale. And this is a pretty rich problem. We'll talk about that today. That's what today's lecture is going to be mostly focused on. When we start to talk about materials, the thing that I want to think about is, we have a lot of different techniques for manipulating the properties of solid materials. All right, so for example, cold rolling is a way of changing and manipulating the defect structures in crystals in order to pile up the dislocations, make them harder, sometimes more brittle, sometimes more plastic, in order to control the properties of the emerging crystal. But when we start to think about things like liquids, it's a little bit more complicated. And I want to ask the question, can we do something similar to what people have done with solid materials in the realm of metamaterials? And so metamaterials, just for those who haven't been initiated, are materials with a mesoscale structure, okay, that occurs on some medium length scale. So it's not what the material is made out of. That could be plastic and wire, but you arrange the plastic and wire in a particular way, and all of a sudden, on a macro scale, you have a cloaking device, all right? Or you punch a bunch of holes in a rubber sheet, and then all of a sudden you have rubber, you have air, but together, when you compress this material, it has a different Poisson ratio or different mechanical properties than either the rubber or the air. And I want to ask the question, can we do something similar to liquids? Can we make something like a viscosity metamaterial? Okay, so that'll be the topic of the second lecture. And then the third thing that I want to motivate is this grand challenge that exists in the field of bioengineering, which is to really 3D print organs. And today, my colleague Larry Benasser, who's in the biomedical engineering department at Cornell, he can already print an ear. This is a fake ear. I mean, it's real collagen, it's real cells. This ear is modeled after his daughter's ear, so it's has a certain aesthetic appeal to it, shall we say? But the real thing about an ear is that an ear is, of course, a static object. Maybe it has to do this, but not a lot more. If you're starting to think about things like cartilage, which have to bear mechanical function, that's a lot more complicated. And so I'd like to tell you a little bit about how we're thinking about these biological materials that are more complicated. And it'll actually be very similar to the way that we're thinking about these viscosity systems. In order to create these sort of engineered tissues. Okay, so that's kind of going to be, that's the overall trajectory. I think we're motivated by really big questions. And the question is, how do we sort of, it's kind of a high level talk, but at the same time, I'm going to anchor it in very detailed examples. All right? And most importantly, I'm going to go as fast as you want. So if something's unclear, just let me know. We'll take a little interlude. We'll explain a concept, anything like that. The whole point, I've seen this stuff. It's for you. So if you're not understanding something, if you're finding yourself like checking your email, ask a question. Like figure out like what you're not understanding. Where are you getting lost? Because the whole point is to bring everyone along. All right, let's start with microscopic machines. So this is a topic that has been around for a very long time. In his very famous lecture, There's Plenty of Room at the Bottom, Richard Feynman talked about the miniaturization of electronics. Okay, the transistor was about this big when it was originally created. And Feynman predicted that as we miniaturize electronics, there's going to be this absolute revolution. And indeed, 50 years of Moore's law has given us just devices with amazing complexity, right? Line widths down to 3 nanometers, right? Little devices where you can pack, hundreds of thousands of transistors in a 100 micron square face. Okay, it's really phenomenal, really amazing. Now, in that same lecture, Feynman also talks about the miniaturization of machines, right? And he actually, this is a funny aside, but he actually had a little bet that if anyone could miniaturize the combustion engine by some factor, he would give them $1,000. And there was this very entrepreneurial guy who actually did it. Okay, he miniaturized it by a factor of 10. And the problem that Feynman had was that the miniaturization was actually like, is a scaled model. In other words, it didn't involve any new physics. It just took the combustion engine and shrank it down. And that wasn't exactly what Feynman was getting at. He still paid the $1,000, but it wasn't exactly what he was getting at. What he was getting at in this lecture of miniaturization of machines is that at the microscopic scale and below, we're going to need to completely revolutionize the way that we make machines. All right? At the nanometer scale, there are no nano screws. There's no nano screwdrivers. And there are no nano engineers to screw the nano screws with the nano screwdrivers. Okay, like we don't have the same abilities at the micro scale that we do at the macro scale. So something fundamentally has to shift. Now, I should say that in the science fiction literature, this is already a solved problem. Okay, so Iron Man has his little nanobots that can form his suit. They can make a material that's hard. They can glom together. We can shrink vehicles down to the size of cells and explore them. But in reality, right, we're still quite far from these types of ideas. So what's the problem? So I'm going to tell you a story in 3 parts. The first part is something that it's not quite, it's not super small, but it's on the way there. It's a sub-millimeter machines, okay, and what we can do there. And the idea behind these sub-millimeter machines is that, like this picture shows, the vision is that they'll have some sort of electronic brain, okay? They'll have some sort of capacity to harvest power, maybe some photovoltaics, okay, like the little black things that you see here, and then some sort of limbs that will allow them to actuate. Okay, so that's the vision. And out of all of these components, the amazing thing is that the brains are actually the easy part. Because Moore's law, like we know how to do this. Okay, so today, my colleagues, Paul McEwen and Al Molnar, can make little devices like these. So this right here is a little voltage meter. It has 2 pads, one here and one here. And the way you measure the voltage between these 2 pads is you have a bank of photovoltaics, a MOSFET transistor, and an LED. And this thing basically blinks out the voltage between these 2 pads. And in addition to that, there are a couple of tabs here. So this thing is built on a sacrificial layer. So when you etch that layer and break off the tabs are kind of like, you guys are too young. When I was young, we used to have model airplanes, and you would have these plastic pieces that came in the frame. And these tabs are like those plastic, like those things that held the plastic pieces to the frame. Okay, so you can break this off the frame, and then you can use it to measure voltages or whatever it is that you want to do. Okay, so how does this look? So here's our device compared against the University of Michigan Micromote and the UC Berkeley Smart Dust. So these are devices that the Micromote and the Smart Dust are kind of like, they're fabricated electronics that are bonded together in a vertical stack. They're the kind of thing that you would put into a pill that you would swallow and would take pictures of your gut. Okay, it's that kind of scale of thing that we're talking about. And the devices that Paul and Al are making are on your right. And the reason you don't see anything is that it turns out that on the penny, there are actually 2 Lincolns. One is on the face of the penny, but the other one is inside the Lincoln Memorial. And if you blow up that Lincoln, that's the devices that we're talking about. Now, of course, smaller doesn't necessarily mean better, right? Like the other devices are much more computationally powerful. but smaller does have some advantages. Okay, so first of all, when you're small, you're cheap. Okay, because the cost per wafer is the same. So if you can make it smaller, every device becomes a lot cheaper. These devices are under a penny a piece. And so someday you'll be looking down at your finger, and that little speck of dust will be one of these devices measuring the pH of your skin. And you'll flash your phone at it, and it'll tell you, oh, your pH is too low. You need L'Oreal cream number 45. And then you'll buy L'Oreal cream number 45, and everything will be good. All right, so that's kind of the idea. The brains are solved. The hard part with microscopic robots is actually the legs, all right? So what we decided to do was to kind of steal technology away from the semiconductor manufacturing industry. And the idea was, could we just build the robot around the electronics making up its brain and then fold it up into an origami three-dimensional robot that could then do its, whatever it is that it needed to do, its actuations. And so if you're going to build paper, legs, origami, you essentially need really good paper. And at Cornell, we're very lucky to have probably the United States' premier research facility for nanofabrication, the CNF. And we've been learning how to make paper. And so here is an example of a sheet of paper that is only 1 atom thick. This is a single sheet of graphene that's cut up laterally into these kirigami toys. Okay, and you can see it over here. This is just stretching like a normal sheet of paper. We've also learned how to grow sheets of glass that are 5 nanometers thick. We've learned how to cut them up so that you can stretch the sheets, and then when you let them go, they come back to their original configurations, right? And so we're good at that part, but of course, we still have that same problem, which is we still got to fold the paper. And so now we have 2 choices. We can either shrink our origami artists down to scale, or we can teach the paper how to fold itself. So we're going to do the second part. We're going to teach the paper how to fold itself. And the way that we do this is by essentially creating electronic paper, all right? So here's our version of paper folding itself. Mark Miskin, now at UPenn, picked up this ribbon with an electrode, and all he does is he changes the voltage on the electrode, and that ribbon folds and unfolds at his command, all right? And the way this works is that we take 7 nanometers of platinum, and we passivate it on one side with an inert material. We then fabricate the device, okay, using lithography. And if we then put it into solution and put a voltage on the platinum, then ions will absorb onto the platinum surface, okay, but not onto the passivated surface. That creates a net stress that's going to bend the beam, all right? If we then apply the opposite voltage, we can drive those ions off of the beam, and now it returns to its original configuration. You then put rigid panels on. Now you've constrained the bending to only occur in the folds that you want. And with that, we've been able to make a whole variety of devices, including this hexagonal fold here, a Muraori, and this world's smallest folding bird or duck, okay? And just to give you an idea, if you also have them pluck a hair from your head and look head on, the footprint of these devices is about a hair's diameter. Right? So that's the scale that we're talking about. Yeah. No, not at this scale, but we'll talk about thermal fluctuations. Okay, thermal fluctuations usually come around at a micron. These are still on the 100 micron scale. Right? Okay, so as amazing as these devices are, this is a picture of one of the devices. You can see here the bright yellow is the 10 nanometer actuator. The dark yellow here is rigid half micron silicon dioxide panels, right? And again, as beautiful as this structure is, it still has this, funny wire hanging from its butt, right? Because it doesn't have an onboard power supply. But we can fix that. We know how to fabricate photovoltaics. So now the idea is that you marry photovoltaics with your actuators. So here's our first ever hello world. Here's the photovoltaic, here's the actuator. And now I'm going to shine light on the photovoltaic. And when I do that, the arm goes boop, 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 boop. Okay, this is not a big wave, but you get the idea. Okay, it's a proof of concept. So now you go to town. You put a photovoltaic for the front legs and another photovoltaic for the back legs, and you make bajillions of them. And you put little paddles where you want the bending to be restricted. And when you're finished with that, you get this one. Okay, so this one we call Brobot. Brobot belongs on a beach somewhere. You shine light on his pectorals and he flexes his muscles. And as amazing as Brobot is, you may notice that he has some defects. All that chest hair, the technical term for that is schmutz. And we've ripped his back legs off. That's not so good. But if you fix all of these and really work hard to create a clean device, then you get this thing. This is a 40 micron by 70 micron by 2 micron robot. It folds itself up and walks across the Petri dish. Okay, you shine light on the front photovoltaics to actuate the front legs, back photovoltaics to actuate the back legs. This is the world record holder for the smallest walking robot. As amazing as this device is, and it is amazing, and I want you to notice the small particles that are near the robot, the jiggling that you see there, that is the Brownian motion that you are looking for. Okay, so this robot is really at the limit of that Brownian motion. Yeah?
By the operation of the device, I'm expecting them to look flat at something, right? If they're not actuated.
No, I mean, you have a pre-stress, so they bend to some amount, and then you actuate around that pre-stress. It's from the fabrication pressure and temperature, all sorts of details that I'm hiding under the rug. Yeah, it's complicated. It took us years to get these recipes, and I'm giving to you all of it in 5 minutes. So there's a lot of details and a lot of really hard work by excellent scientists at CNF, figuring out which materials work. We tried many materials before we got to platinum and titanium for the passive layer. Yeah. Yeah, so these actuators are limited by the viscosity of the fluid that the robot is in. But we have recently made actuators that work in vacuum, and those can go at 10,000 hertz. Okay, so it's inertia limited. All right. As amazing as that robot was, it's still just a marionette, which means that you have little strings pulling at the little limbs, right? In our case, the strings are lasers. We can get rid of that by essentially fabricating a brain for it. And so we collaborated with XFab, which is a commercial foundry. This is what silicon brains look like. And what we did was we created, in this case, a very simple brain that has photovoltaics that power it and a CMOS circuit, same kind of electronics platform that powers all of our cell phones. And this particular brain just puts out a clock signal. In other words, it's just a clock, and it puts out a voltage pulse at different phases, depending on which pin you hook up to. And depending on which pin you connect, you change the frequency. Okay? And so then with this one, with ClockBot, we can essentially tether it, depending on the pins that we connect to a hexapod robot. And this is what that robot looks like before we release it from fabrication. And you can see it has 6 legs. This is the circuit over here. These are grounds for the electrodes. And when you release this robot, which we lovingly call Antbot, has 6 legs and kind of crawls on its own. So you just put it in light, and then the brains power everything, and it just goes. Okay? So this is the kind of where we are. There's actually a very large group of us at Cornell who are now designing next generation circuits, designing next generation actuators. There's a lot of work going on in making cilia, making metamaterial sheets of these kinds of robots. And so that's another talk. I don't want to go through it, but I thought I'd be remiss if I didn't sort of talk about these students' work and the amazing things that they've done on the way down to the micro scale. So I'll pause here and just take any clarifying questions. Yeah.
Like bacteria.
Yeah, if you want to swim, we have swimmers. So you can swim in a number of ways. You can bubble yourself across. There are other actuating surfaces. So cilia are effectively a way of pumping fluid. If you put those on a chip and get it to go, then in principle, we'll be able to swim. I'll show you another swimmer later on here. The other thing that we're doing is, like I said, we have actuators that work in air or vacuum. They actually work in any medium. We're trying to make a microflyer, like a real microflyer on the order of 300 microns for each wing. Okay, so it's smaller than a fruit fly. So all of those are fair game. Yes. Okay, so again, there's a lot of work going on in this area, and I'm happy to like chat if you catch me afterwards. But I want to talk a little bit more on sort of the concepts of machines at the microscale. And I want to start by sort of going to the very, very smallest scales, which is the atomic scale. Yeah.
So you are putting micro that is it possible what about that?
Yeah, so batteries at this scale, like if you have a 10 micron cube battery, that gets you about 10 minutes for the power that we need. There's not a lot of time. There are other things that you can do, like you can make magnetostrictive materials interlaced with piezos. That's a method for actuating you put a magnetic field that cycles, it actuates the magnetostrictive materials, which then compresses the piezos, which then delivers power. So there are things like that that we can do. But light is super easy, okay? And right now there's so many fish to fry, so many different proof of concept demonstrations to do that we're leaving the harder stuff for later. Okay? Any other questions? Okay, so let's go down to the atomic scale and talk about that for a second. So in 2016, these three gentlemen won the Nobel Prize in chemistry for making atomic scale machines. All right, and this was a tour de force in chemistry. Okay, really brilliant organic chemistry to fabricate these molecules. Let me show you some of these devices that they've made. So over here, what you're seeing is like a loop around this rod-like molecule. And this machine, the way it works is that the loop moves from one side of the molecule to the other. And so it's kind of like a two-state machine that can toggle back and forth. This one, I think, is interesting. It sort of has two rings that can sort of rotate past each other. And on the right here, I'm showing you the world's smallest and possibly slowest car that's ever made. The way this car works is that you dump in some chemicals and the wheels rotate by like 30 degrees. So you just keep like oscillating this chemical reaction to get it to crawl across a gold surface, okay? And people have been making these kinds of atomic scale machines, and really they've been building some really fantastically clever designs. So for example, out of DNA, you can now make structures using DNA origami. So people, for example, have made little capsules that can carry material. They've fabricated things that sort of look like a bow and arrow, though I'm sure they don't function that way at the microscale. They've made mechanisms that allow these machines to open and close. And so this is one way that people are doing it, just by sort of fabricating or thinking about mechanisms that we implement at the macro scale, and then try to think about how to implement that at the micro scale. But to me, a lot of these efforts leave me kind of cold when I think about the amazing machinery that already exists at this scale in each and every one of us. Okay, so in your body, right now, there are little highways that are being built and disassembled. There are walkers that are carrying cargo from one location to another, right? These kinds of protein machines really beat the pants off of anything that we can do with the chemical reaction. And in particular, if you're thinking about pitting, 9 billion years of evolution against a poor graduate student who's there for 7 years in a chemistry lab, like, I just feel like it's unfair, okay? And it's not to say that the things that they're doing at these molecular machines aren't amazing. They are. But there's something here that just seems like such a more powerful machinery that's already developed. Okay, so one way that you could start to think about this is to sort of make machines by hacking biology. And like I said, people are doing that with DNA and structure, but I think you can go deeper along those routes. And possibly the deepest area that I've seen, which is really spectacular and which you should all be aware of, is de novo protein design. Okay, and so what's the idea here? This is the work of David Baker and colleagues. But the idea is the following, that these days it's trivial for us to make amino acid sequences. Okay, we can make anything you want. You can just dial it in and we can deliver for you an amino acid sequence, and then that sequence will fold up into something like, not necessarily an active protein, but some structure. And then the idea is that that structure could act as your machine. Okay, that machinery exists. It's very easy to make. The problem is, what should we make with that? And for many, many years, we've just been guessing. And the revolution that's happened over the last decade, or 5 years or so, is the advent of AlphaFold. So how many people have heard of AlphaFold? Okay, so everyone's heard of AlphaFold. Okay, so good. So AlphaFold is a machine learning, algorithm. You feed into it all the known protein structures, crystal structures that we've solved for, and it spits out at you, if you give it now a new random sequence, it spits out for you structure. And the way I like to say it is that, like, I had a conversation with Michael Brenner, and he said, AlphaFold, like, it can't even predict the symmetry. Okay, you tell it to produce something with a 6-fold symmetry, it gives you something with a 7-fold symmetry. Like, there's a lot of problems with AlphaFold. But if you talk to David Baker's people, they'll tell you that before AlphaFold, their success rate at making a new structure that had never been done before, not a derivative, but a new structure, was like less than 1%. And after AlphaFold, it's like 50%. Okay, it's a complete game changer. So who cares if you folded the right structure? You got something. As an experimentalist, that's gold. All right, it's really changed the world. Like the world of de novo protein design has really changed. And the basic idea here is that if you take a look at this diagram at the top, this circle here might be the place that biology has had a chance to investigate up until now. But who's to say that the next miracle cure doesn't come from a place like this that has never been investigated by biology? All right, and that now is doable. And we have all of the experience of biology, that 9 billion years of evolution, to teach us how to build these structures in order to explore this kind of area. And so this is what is now happening in the field of de novo protein design. People are co-opting this machinery to make these kinds of structures with the hopes of making machines. And again, beautiful structures that have been made. If you haven't read papers in this area, I highly encourage you to do so. Okay, so where do I want to come in with my 2 cents? And where I want to come in is I want to say that, making structures is not the same thing as making a machine. And I feel like one of the things that's still missing in this field is the problem of how do we make machines at these nano and submicron scales. So what do I mean by that? When you think about a protein is not just like a car. You don't have like windshield wipers, which then connect to something, and then like the wheels don't talk to the windshield wipers. A protein is like an everything talks to everything machine. It's actually quite complicated, right? You move, like Andrea was saying, you move something over here on this end of the protein, something changes on the other end of the protein. It's all mixed together. And that creates a bunch of challenges. There are many parameters that you have to understand in order to figure out how it functions. There's a lot of variability, like there are mutations. There's a lot of noise at the nanoscale, right? You're subject to thermal fluctuations. You have limited control. And so one of the things that we wanted to think about was, could we design paradigms for working machines at this scale? Okay, what would you need as a paradigm? And in order to kind of explain what I mean, I'm going to give you an example project that we did in my lab. And it really built off of this work by Tom, which suggested that, critical points in bifurcations are really interesting places to work around. And so I'm going to explore that idea and try to see where we go from there. Okay, so I want to make a machine, and I want to think about critical points. So here's a very simple machine. This is a video of a bird, a hummingbird, that is, how do I make this? Yeah, okay. So watch this hummingbird. It's going to cock its beak open, and right here there's a fly, and then snap, the beak shuts. Okay, and I have a little demo to demonstrate this. Okay, so I want you to notice what's going on here. So the bird opens its beak, okay, like this, and then, oops, and then snaps it shut. Okay, but notice what, look at how amazing this is, right? First of all, I'm not doing very much with my thumbs. Okay, I'm just doing like a little tiny motions. And how much is that beak moving? Oh my God, it's moving an enormous amount. Okay, that's a very useful thing for a machine. If I had to move my fingers way out here beyond where the beak lay, right, I'd rip the beak apart. So something about the ability to convert very small actions at the base of this beak into this motion, right, is really key to making this function. And the guy who figured this out is Andy Ruina at Cornell. And what he pointed out is that the beak is a good example of a machine that is built around a bifurcation. Okay, so how many people have heard of bifurcations? Okay, most everybody. If you have questions, please ask. But the basic idea is that if I solve for the positions, something, can I play it again? Yes, of course. Let's see if I can. Okay. So here's the little fly, and there comes the beak, and snap. Okay. And so what Andy pointed out is that this beak, basically, when I get it to this cocked position, it has two solutions that are stable. One of them is this one. Okay, but with a little tiny bit more, I can get it to snap into the second stable solution here. Okay, so what you do is you go around a bifurcation in the equilibria states of the states. So this is a loop. So you cock the beak when you get to here, and then you move along this direction until you run out of solutions. Now you fall off of the upper branch and you hit the second branch. All right. And what's interesting about this loop, this is the loop viewed from the top down, is that as long as you encircle the cusp, right, you're guaranteed to have this motion happen. Guaranteed, right? That means that if the hummingbird was tired that day and it didn't quite actuate the beak in the right way with its muscles, or if it was slightly malnourished when the beak was forming, as long as you circle this cusp bifurcation, you are guaranteed to have slow cocking of the beak and then snapping shut, right? And that is a very powerful idea, right? For many, many years, physicists have shied away from working with and designing things around cusp singularities because at the cusp itself, everything becomes super sensitive, okay? Noise gets amplified. And so you talk to physicists and say, oh, that's a terrible idea, noise gets amplified. But if you're working near the cusp bifurcation, okay, that amplification can be your best friend, right? So what I'd like to do now is I'd like to show you how we're going about thinking about how to use this concept to make the microscopic machines that we're thinking about. Yeah. Well, I mean, they put together a mechanism for the jaw and the muscles, and they put together like an actual like diagram. It's a great paper. Okay, I highly recommend that you read it. I don't think I have the Andy Ruina bird beak. You get it. I'm sorry, I don't have the citation. Okay, now if I'm going to try to make protein machines, okay, proteins are really complicated. Why is that? Because proteins, amino acids are hydrophilic or hydrophobic. They have screening, right? There's charges in the fluid, ions in the fluid that screen the interaction. That's a really complicated system to try to figure out, especially with simulations. It's really hard. So we're going to go back and do a simpler problem with magnets. And the reason we do it with magnets is that there are no magnetic monopoles. If there's no magnetic monopoles, you can't screen magnetic interactions. So the interaction strength between different surfaces, all you have to do is count up all of the dipoles and sum them up at the location that you're looking at. Okay, so for us as physicists, we're going to be able to uncover this paradigm, okay, but in a simpler magnetic platform so that we don't have to deal with all the complications of the bi-screening lengths and all the rest of that stuff. Okay, so here's our approach. We're going to make a very simple machine. In this particular case, I have one panel with a set of magnets. So I embed magnets in the panels. This one has a north, north, and then the rest of the magnets are south. This panel has north, 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 and the rest of the magnets are facing south, yeah, or showing south. This panel, I'm going to be able to control in the X and Y direction. That's my control parameters, okay? Just like in the hummingbird, my fingers were the control parameters, and the beak was rotating. Here, the X and Y, we're going to use little micrometers to move our macroscopic panels, and we're going to let this panel swing in theta. And we're doing this all macroscopically, okay? So the vision is to eventually shrink this down to the microscopic scale, but right now I'm going to show it to you in a macroscopic system, okay? So this is an axis that's a free hinge axis. And the idea is that by playing around with the X and Y positions of the first panel, I can effectively create different configurations for the most stable states. And that's going to allow me to switch from a state with a high open angle to one with a low open angle. All right, so let me kind of take you through this. So here's a video of the apparatus. You can see a little rod here. This is on an air bearing. It allows one panel to swing open. At the bottom, there's a little there's a dash pot with some glycerin to make everything a little bit more viscous. This panel in the back is the one that I'm going to move. And for this particular array of magnets, the equilibrium surfaces are described by this cusp, this surface with a cusp in it. Okay, so the idea is that just like the hummingbird, I can open this slowly, and then I can jump down when I run out of solutions. Okay, and what I'll do is I'll play the video for you, and we'll kind of try to track what's going on this diagram. Okay, so here comes the panel. I've moved down in Y, okay? And then at some point, I moved over in X, and now this back panel is moving up. And at some point, this thing is going to swing right open, okay? So it moved from a position where it was closed, and then it swung right open. It moved up to the upper surface. Okay, so by taking loops, either clockwise or counterclockwise, you can jump from one branch of solutions to the other, okay, in this smooth fashion. So I'm going to play the video once again. Okay, so here I'm closing it up, okay, and then I move in this Y direction. I'm moving the back panel down. At some point, you run out of solutions, boom, you jump up to here. Okay, right around there. See it? Okay. Any questions? Is it clear? Thumbs up? Okay. Okay, so again, there's some nice things about this. And the way I'm going to describe this diagram, yes, sorry. What you're doing is you're changing the XY panel's position, right? This panel's position relative to this one. And you have a particular magnetic pattern so that when you sum all these up, you end up getting a equilibrium surface with this thing either closed or open. So in some sense, if I have a magnet here that's attracted to this one, if I move this one down and this one is repulsive, it'll want to open up. Okay, so that's like mechanistically what's going on. You're changing the surface that this one is seeing, okay, by moving this in X and Y. But the thing that's nice about this particular pattern of magnets is that I've created a surface with a cusp, and as long as I operate around that cusp, I don't need to move my X and Y very much in order to get huge changes in my angle. That's one of the key things. I saw somebody besides Eric. Eric.
Yeah, so I wanted to talk earlier today. He was talking about systems where you gain a lot by increasing the dimension of your phase space versus don't. And I was wondering if you had any comments in systems like this, like is it to go to high dimensionality or is it
We'll talk about that in a second. Yes. When we get to slightly more complicated machines. Great. So because we're going to talk about slightly more complicated machines, I want to introduce kind of a nomenclature. I want to describe what you're seeing in this 2D diagram. So this whole thing is going to be collapsed onto a 2D diagram. I'm going to paint my trajectory here in this square loop by the color that tells you what the opening angle is. Yeah? And the point is that when your opening angle is high, you jump when you hit this line here, okay, the brown line, which denotes the high limit of the solution space. Okay, whereas down here, I have, if I'm blue, then I hit the blue line that denotes the limit of the transition space. Okay, so this is the blue line, and this is the yellow line. Those are joined at the cusp. Okay, and so if I go around here, okay, what happens is that if I'm on the yellow, I don't transition until I get to the yellow line. If I'm on the blue, I don't transition until I get to the blue line. Does this kind of make sense as a language for us to speak about? Okay, because I'm going to use that coming forward. So any questions about that? Right? And the point is that because these transition points close up like a parabola or some sort of function that has a very steep slope at the critical point, okay, it opens up, right? So if I have my critical point splitting like this, right at the critical point, this slope is very steep. And so that means that I don't need to move very much in my control surfaces in order to get a very large change in my opening angle. All right? So that's called the lever advantage. And when you're working around a critical point, you always get a lever advantage, okay? And if you go too close to the critical point, everything becomes infinitely sensitive. But if you're at some distance, that lever advantage can be used to the benefit of the designer, the organism, whatever, okay? And we'll talk about some of those ideas in the third lecture where I talk about biology and how biological systems use this phase transition structure. Okay, this is the same structure that you would get for second order phase transitions in order to gain their lever advantages for their materials properties. Yeah.
On the same side as the yellow part of the cusp line.
You mean, why is this part? Yeah, so if you're going in this direction, you're on the bottom surface. So that's why this is blue. If I go up here, you start to go from blue to yellow, okay, continuously. And then you're on the upper surface, you're on the upper branch, and you don't cross over until you hit the yellow cusp line here. Boom. Yeah. Yes, but it'll be at a different point. There'll be a hysteresis.
That can I expect that at certain part, I don't think anything will look like that in the order. Like the bifurcation point there.
Yeah.
Can I say, is it possible to have something like this?
This cusp is equivalent to this point right here. Okay, so right at this point is that cusp. So the fact that these open up, okay, the fact that these open up is what gives you the lever advantage. Okay, good questions. More? Good. Okay. So two things that are useful here. One is that we have the topological protection. One is that we have the lever advantage. Okay, that's kind of the benefits of working around these cusps for machines. Okay, so now, and you know, like we did some work on figuring out what the power laws were as the thing was going to the cusp, but that's not so important. So how do we design more complicated machines? You know, two-state machines is one thing, but if I want to design more complicated machines, I need more states. So we did this originally by trying to use like Monte Carlo simulations to like figure out which pattern of magnets would be good to get three stable states. Okay, and when we were doing it, we needed a panel with 20 by 20 magnets for the control surface and another 20 by 20 magnets for the other panel just to get three equilibria. And it's very hard to convince students to glue 800 magnets just to get three equilibria. And that, of course, is not a good scalable way, right? I mean, if you now have to get 4 equilibria, God help us. So we had to go back to the drawing board. If you want to create something like this butterfly bifurcation, where you have 3 states, a large, a medium, and a small. Okay, so in principle, the idea is that if I had something with 3 states, there's many, many more paths that I could take. So here are the boundaries of the states in these colored lines, and this highlighted thing here is the pathway, right? So if I have this kind of structure that I'm working around, then I could, for example, have a transition for the purple one. So if I'm in the small state, I don't transition until I'm here. Boom. Then I go into the medium one. Then I transition again here into the high state. So that's a 3-state system. But notice that if I go backwards, I get a completely different behavior, right? So the idea is that by choosing loops around all of these boundaries, you can create machines that can transfer from one state to any of the other states that you want, just by configuring the pathway, right? Okay, so how do we find these systems? How do we get to a system with 3 stable equilibria if it's so difficult to design? And the answer was not to necessarily have more magnets, although that's certainly one way to do it. But the idea was to release the parameter space. So this is what we were talking about, and this is what Andrea was talking about, to allow these magnets to drift. So instead of this magnet being tethered to this location, we now introduce 2 more parameters, the displacement in x, the displacement in y, same thing for this one, in order to allow for more phase space that we can investigate, okay? And then this is where another problem comes in, which is, of course, the more phase space you have, the more difficult it is to find points in that phase space. And if you want to make, let's say, a cusp with not just 2 surfaces, right? Not just 2 equilibria, but let's say 40 equilibria, all coming out of a single cusp, so that I can transition between 40 different states, all right? That would be very difficult to find in a very large parameter space, okay? It becomes exponentially rare. So you do not want to just do a random search through space. That's not going to work. And so what Itai came up with is this idea of, instead of trying to solve all of the constraints at once, the idea was to go one at a time. So you start with some n-dimensional phase space, and you implement one constraint. So finding a single equilibrium in this high-dimensional space is pretty easy, right? And if you implement the constraint, okay, that dx by dy is equal to 0 here, you can essentially reduce the dimensionality of this by the number of constraints that you have, by 1. And so you move from an n-dimensional space to the n-1 dimensional surface associated with this manifold. So far, so good? So you kind of do gradient descent on this space until you find the surface, and then you do exactly the same thing. Now your surface becomes your new manifold, and you implement the next constraint, which is that I need a maximum. And then you go again until you get your second minimum, and then the maximum, and then the minimum. And you build these up one at a time. So instead of your search being in a huge phase space, you're really only doing a linear search, okay, at any given point. How's that? Yes?
First step is like a whole bunch of points that you could have started with. How, like, do you get the same configuration at the end?
No, but you can always move along that constraint until you reach a higher order bifurcation. And so you might end up, if you have a different initial condition, you might end up with a different bifurcation, but you'll always end up with the higher order one. Okay, so if you have enough parameters, okay, if you have enough parameters in your phase space, you can always end up at a higher order bifurcation that you're looking for, not necessarily the same one. Okay, so the idea is that you follow these one-dimensional searches. I can do it here. You follow these one-dimensional searches until you reach like the saddle known surfaces. Then you follow that until you reach the cusp. Then you follow that until you reach the butterfly. And this you can do ad infinitum. So if you want a higher order bifurcation, you just continue along this line. Okay, so far so good? All right, so here it is. This is an example of what one of these butterfly bifurcations looks like. It's not symmetric, so it's a little more interesting than the one that I showed you previously that was completely symmetric. But here, what Itai has done is identify the surfaces of the transitions. All right, and the pathway is again labeled in this shaded region over here. And the idea is that if you follow this pathway, then when your pathway has the same color as the surface that it intersects, that's when you're going to get a jump. All right? So I'm going to show you a movie that combines everything. So again, the control surface is in the back. This time I can control X, Y, and a little bit of Z, all right, in order to make it a little bit easier for Itai, although we can do it with just X and Y. And then up here, I'm showing you what the energy landscape looks like. So in this particular case, there's a minimum when the panel is closed. That's where the panel is. And over here with the dot, I'm going to show you where I am along this trajectory. Okay? And so here we go. So here is, we went along here and we got a transition to the open angle. And then you go here and you can see that in principle, we should have transitioned there, but something went wrong with the way we glued the magnets. It happened over here. But that's okay. That's topological protection. We glued it a little bit wrong. Okay, but we still got the transition. And then you go to over here until this disappears and you're back in the small angle. Okay, so I'm going to play this a couple of times just so you can see it. But this is a way of designing a machine now, okay, but by having everything talk to everything. Okay, all the magnets talk to all the magnets. All right, and the principles, again, are the topological protection and this ability to have the lever advantage of a small displacement leading to a large change. Okay? All right. Let me play it one more time, and then I'll pause for questions. So here's where that minimum disappears. Now the system is here in the open angle. I keep going, and at some point, it's predicted that you transition here, wasn't quite there because we glued the magnet a little bit wrong. Boom, it happened there. Okay, now it's back to a medium angle. It's not completely closed. You keep going, you keep moving this bottom surface, and over here, you'll see, boom, now it's closed, right? So far, so good? Thumbs up? Okay, so now, yeah. Yes? How to control that distance? Everything is talking to everything. Magnetic fields are not screened. So even at the open angle, these magnets are talking to one another. Okay, there's no magnetic monopoles. So you don't screen anything. Yeah. No, it's that you're working around a critical point with 3 branches. Okay, so as long as you're working in that vicinity, okay, you're always guaranteed to have that topological protection. There's always going to be 3 branches. If I glue the magnets a little bit wrong, the branches, instead of looking like this, will look like this. But there'll always be 3 branches. Yes, you do need to design the pathway to do that. Okay? Okay, so let me just take a step back. Whether or not proteins work this way, I don't think I hear people talking about it. Some people do think that proteins jump between states, but of course they're very thermal, so it's hard to tell. It's hard to make those measurements. But this idea of sort of thinking about designing these de novo proteins, or thinking about whether biology could have, for example, evolved one protein function, and then instead of trying to evolve a protein that can do multiple things all at once, it keeps this and then evolves a new function, okay, and keeps that and evolves a new function, okay? That's something that I think is a very powerful, robust sort of idea, and I'm interested in knowing whether or not it has applications to things like evolution of proteins, maybe even evolution of function in other organs. Like when animals developed color vision, they didn't develop it all at once. It usually goes one color, then another color, then another color in this sequential fashion. And so this gives you an idea of how that optimization can happen. Like how do you search amino acid space to create a receptor for light that can do 4 colors? Instead, maybe you first do 1 color, keep that because it's evolutionarily advantageous, and then explore the phase space around this surface, okay, to develop the next color, and so on and so forth. Okay, it's an idea. I don't know. Okay, so we've thought a little bit about noise in these systems, and the calculations that we've made say that if your system is about 100 nanometers, that's the smallest that we can sort of make it without being too affected by thermal noise. In a 100 micron machine, we can create 20 states, okay? And part of the problem is the more states you make, the less the barriers between the states. So energetically, there's a limit to how many states you can have in one of these machines, about 20 for a 100 micron machine. And yeah, okay. So I think that's most of what I want to say there. So yeah.
Specific to the magnetic.
Yeah, so what we're talking about are with magnets, which have a limit, right? We cannot make a stable magnet below 30 nanometers. Okay, that's when the molecules will, the system will become paramagnetic. It won't maintain its magnetic field. Okay, so now the question is, can we actually build these kinds of things at the microscale? All right, so back to CNF. And now this time, the building blocks that we're thinking about are magnetic. Okay, and the key technology that we've been playing with was really developed by this brilliant researcher, Jisai Kui. He beat us to the punch. Okay, so no bones about it. This guy was brilliant. He did it I think he did it alone, but it was in Bradley Nelson's lab at ETH. Anyway, he's amazing. And what he figured out is that you can make single domain magnets at the nanoscale by essentially making these pill-shaped particles. Okay, so you can see this one over here is short and stubby. This one is long and thin. And the idea is the following, that if you want to create some sort of pattern, what you do is you build it out of both of these kind of magnetic domains. And the short and stubby ones, they have a lower coercivity. In other words, these are single domain magnets, so their magnetization aligns along their long axis. But if they're short and stubby, it's very easy to flip them to the other direction. If they're long and thin, it takes a really big magnetic field to rotate them around. And so what you do is you first put a magnetic field that aligns everything this way, then you reduce the magnetic field and only flip over the short and stubby ones. All right? And in that way, you can create whatever magnetic pattern you want, and that allows you to start programming the magnetic fields in these systems. All right? And so I'm going to show you a couple of things that we've done here. It's not a huge amount, but kind of gets you a little bit of a taste of where we're going. Okay, so for example, we've made little magnetic panels. These are the little the nanomagnetic domains. These panels have basically 4 layers that they're made out of. We release them on the surface of water, and then they can self-assemble into little structures. And I'll give you like one example for why this is a powerful strategy. So once we release them, if we apply a magnetic field, we can rotate these panels and they can do some mixing. But if we start to think about assembly of these, and this is work that we're doing with Michael Brenner's group, and Chanze is part of that team. The idea is that if these monomers have a net dipole moment, then they'll couple to the magnetic field and they'll spin. But if the final structure that we want to make doesn't have a net moment, then it'll decouple from the field. All right? So this is a way of guaranteeing production of our end product. Okay, so you just rotate these things, and whenever you want to break them apart, you just increase the magnetic field. This one has a net moment, it's going to spin. This one has a net moment, it's going to spin. So these will break apart into monomers. But this one doesn't have a net moment, it's not going to spin. And so with that, you can essentially make these particles sort of, if you cycle the field up and down, so same frequency, but just magnitude of the field, you can get these particles to assemble when the field amplitude is low, okay? And then you see these particles still rotating around. That's because the field is still spinning. And then you increase the field, you break apart everything that you don't want. And with this, you can basically avoid kinetic traps. So after a few hours of this, you can get 95% success rate in all of your self-assembly, okay, which is pretty remarkable for self-assembly. Usually in thermal systems, it's very hard to get these kinds of completion rates. Okay, so you essentially kill all of the local traps. Okay, so if we want to make machines, so that's kind of a little aside on self-assembly. But if you want to make machines, you got to do the paper. You got to have little things that connect them to one another. So here's a little machine that we've been making, where we essentially have little bars that we put our little nanomagnets on. And in between, you can see these little yellow ribbons. That's the 2 nanometer thick glass that's holding this particular panel together. And because this has a regular spacing, this ends up being a diffractive object. And so one of the things that we've done with these little magnetic systems is really thought about, can we try to build robotic microscopes or diffractobots that we could position, that could measure forces, that could do some optical tuning. And I'll show you again just snippets of this. So here's an example of a diffractobot. The red shows you where the magnetic panels are. Here are the little magnetic pill-shaped particles. And the idea is that these are oriented in the opposite direction, so that when we actuate the Z field, this thing will fold up and then fold down, right? It just goes up and down. If we do something a little bit more clever, we can, and as it folds up and down, the spacing of the line between where the light can get through gives you a diffraction pattern, and that's what you're seeing in the bottom spot over here. If you do a little bit more, if you put an X component to the magnetic field, you can get this thing to walk. Okay, so here's a movie of one of these things walking. Here's an example of how that works. It's kind of like the way an inchworm works. Okay, so you apply the magnetic field as shown by the arrows, and you get this thing to walk across. And you can do this at 1 hertz, 2 hertz, 8 hertz. The smaller the object, the faster it can walk because there's less resistance from the fluid. We can also do this with our big diffraction grating. So you can walk the diffraction grating anywhere you want and then diffract light in that vicinity. Here's an example of a robot going through a maze. So you can control not just the X, but both X and the Y, and get this little diffractobot to move through the maze that you constructed for it. So it's cute. And you can see there is another diffractobot, but because its steps are smaller, it's going through a miniaturized version of its own maze. Okay, but this is applied through a hexapole magnet that's making all of the diffractobots move at the same time. All right. You can also get swimming. So here's a diffractobot that is swimming. Okay, so what it does is it swims, and then you flip it over so that its arms are back in front, and then it swims again. And by doing that, it can essentially beat the scallop theorem and swim through a viscous fluid. All right. This is a vertical swim, so now it's going up. And I should say that these diffractobots are much, much smaller than our previous world record holder. So these are going to blow, once we publish this stuff, these will blow the original record holder out of the water, because we can make these down to a micron in scale, and we can still operate them using the magnetic fields. Okay. We can make microscopic lenses out of them. So for example, you can have a Fresnel lens instead of like the optics that you have with a microscope. If you put the Fresnel lens on, then you can walk your robot, shine a laser through the Fresnel lens, and get illumination that beats the diffraction limit. Here is an example of one of these robots. Let's see if I can get out of this. Nope. I don't know how to play these movies. Gotta get out of this. Escape. There. Okay, so here's one of these objects moving. And if we have this thing as a more complicated magnetically patterned robot, you can get these beautiful diffraction patterns that oscillate back and forth as the robot is being actuated. And these things can both actuate and expand and contract. They can also move. You can change their frequency. If you start introducing magnetic fields in the X and Y direction, then they'll start to locomote along those directions. Okay, so here we go, and now it's locomoting up. And then you switch the phase, it locomotes down, and you get the idea. And you can, so these are some of the other designs that Conrad made. And these are the kinds of diffraction patterns that you get from the various designs. So again, very beautiful. And you can do things like SIM stands for interference microscopy. Damn it, I forgot. I'll remember. Like, so this is the equivalent. It's RSIM. Okay, so the idea is that you interfere a diffraction pattern that's on the robot with the diffraction pattern that you're trying to illuminate. Okay, so I'll go to this location and see if we can, oh, won't let me. Really? Come on. You don't want to do it. Okay, we'll have to play it. So in this particular strategy, what you do is you interfere a diffraction pattern that's on the robot with a structured pattern that's on the surface that you're trying to image. Okay, so when the robot goes through, depending on the orientation of the robot, you get a moire pattern. And by rotating the robot and using all of the moire patterns, you can reconstruct the structure that's underneath. And so this is a movie that shows how that works, structured illumination microscopy, thank you. And we'll show you how one of these robots can be walked over to one of these arrays. And then if you have, for example, a resolution marker, this is one that you can see. And what we're going to do is we're going to move the diffraction surface onto these lines, and you'll see the diffraction pattern. Okay, so here it comes. Okay, and so as you rotate the robot, you can see bright and dark spots that are on the surface there. See that moire fringe pattern? And now you can do the same thing, but now with structures that are sub-resolution. And when you do that, then you can really, you get the same types of moire patterns, but now with structures that are much, much smaller that you can image. And I don't know where I am. There's a lot of this video, I guess. All right, let's move on. Okay, so the idea is that if you did this with a structure that you couldn't illuminate, now with this structured illumination microscopy, you can get back out the length scales of the structures that you're looking at. And we've even done something like this, which is 4 posts in an SEM, which looks like just a single pillar. But if you resolve it with the robot, you can see the 4 posts in the reconstructed image. Yeah. Oh, because my laser's back off. Yeah. So here, these 4 dots they look like a single dot until the robot moves over them and reconstructs their image, and then you see that there are 4 pillars. Or here, you can't see any images of the structure that's underneath here until you reconstruct the image and generate the structures that are there. Okay, so that's what structured illumination microscopy is, and the idea is that you could send bajillions of these robots walking across your surface and image all of them, and then you'd be able to get some structure of your surface, right, very rapidly. And we've done things like make Fresnel lenses that are pretty complicated to change like the focal point. And so these are the kinds of machines that we might put at the end of a fiber in order to get a lens on a fiber that would allow you to have more functionality when you're sending your light through. Okay, so that's kind of a little aside for some of the machines. But again, these are pretty simple machines. They're not the same kinds of machines that we described. So I want to do one last little bit before my time is up, which is to tell you about how we're getting to the machines of the kinds that I described. So here, what we're doing is we're combining the nanomagnets again, and now we have a little ribbon that connects these panels. And so we can create panels. In this case, we have sideways, sideways, up, and sideways. And if we apply a, I see I have to do that again. If we apply a magnetic field, then you can get these panels to move. Okay, oh, that's horrible. Let's do that again. Okay, then you can get these panels to move, all right? And even lock up because of their magnetic domains. And so these stay locked even if you don't apply a magnetic field until you apply a magnetic field that is strong enough to pull them apart. Okay, and so now we're starting to get into the kinds of machines that have multiple states. Again, very simple, not like the complicated proteins that we're talking about, but it lets us sort of investigate these paradigms. And this time, all of these panels are now at the 10 micron scale. All right, you can have panels that can rotate from one helix to another. Okay, even though the magnetic field is exactly the same. So this is a system that has either one chirality or the other, even though the external magnetic field is identical. That's 2 states within the same configuration of the magnetic field. And here's one where Melody put these panels together, and you can see that we're playing some games. So the idea is that you can take this panel and you can rotate it in plane. Okay, it'll then attach to here. Okay, because the magnetic dipoles are opposite. Then you can apply a vertical magnetic field. It'll want to spin out by itself, okay? You could bring it back, right? So there's all these different configurations that you can start to play with by twisting the ribbon, by actuating the magnetic field. And this is our attempt at describing the loops that you're seeing. Here is the magnetic field in the azimuthal direction, the sort of angular magnetic field, and BZ is the vertical magnetic field. And the vertical axis is the panel normal vector, okay, which is telling you which way the panel is oriented, right? And then the color represents the twist in the cable, okay? So it's kind of like giving you a trajectory through this phase space. And now you're starting to design the kinds of machines that we've been talking about, and you have this sort of capabilities for patterning them and starting to investigate and play with them in order to see whether or not we can develop either this paradigm of a critical point breaking up into multiple stable states or other paradigms, right? If you have other paradigms and ideas, we would love to investigate them in this kind of simple platform that allows us to explore this interesting phase space, okay? So with that, let me just hark back to Richard Feynman's idea that really machines at this scale need to be designed differently. We can't build them the same way that we design machines at the macro scale. I think we need paradigms for actuation and for function of machines at this micro scale. Those are missing. I've given you an example of one of them. And I think it's really going to be interesting to see whether there are others. But we're going to need them because there's no way that this field of de novo protein design and all the things that we're trying to make at these microscopic scales in terms of machines are going to be able to function, really have, working function if we can't, have a principle to work around as we're designing them. And I think that's a job that physicists can play a role in and have a very big impact. So with that, I'll put up some of the papers and thank you for your time and take any additional questions. Yeah, when they form a tetramer, that's the target structure. So the paradigm, I kind of went through it quickly. It's didn't fit into the theme of machines, but the self-assembly, you could self-assemble machines. So we've thought about how do you self-assemble a machine and then get it to operate. But one of the problems with self-assembly is that you get stuck in intermediate states. That's what gives you the long assembly times in thermal systems, okay? It takes forever. And we wanted to get rid of that. And the way we thought about getting rid of that is to say only the structures that are intermediate and the off-target structures will have a net dipole moment. So a single panel has a magnetic components that go this way and that way. So it has a net dipole moment. A dimer has a net dipole moment. A trimer has a net dipole moment. But the tetramer, which is 4 of them together, that net moment is 0. So if we rotate the field, that it's not going to do anything. It's going to decouple. It's like you have a quenched state that doesn't couple to the thermal noise. And so that's how that works. And then whether we can, design machines that can both self-assemble and operate with the magnetic field, that's still something that we're trying to work on. But this idea of connecting them with tethers, like this very thin paper made out of glass, that seems to be like a pretty viable way forward, okay, to design the equivalent of like an amino acid sequence with specific binding interactions between the panels, because we can make complementary bonds between them and try to explore that phase space. Okay. Good. Other questions? The microscopic robot with electronic control? or the ones that I just showed you. Yeah, those are not so hard. Those we do at the CNF, and we can do them in like 3 days. But we don't make one. We make thousands, right? Millions on a single wafer. So the idea is that in this world, you don't just make one design at a time. You make a bajillion different designs, you put them all on the wafer, and then you have experiments to last you forever. If you're talking about the electronically integrated microscopic robots, for that, we design the circuits. That takes a while. Then we have to fabricate them. That takes about 4 months. So that's a much more extensive effort. Like you really need to really think about what you're going to do. What are the electronics that you want in order to, what are the behaviors that you're programming? And we're getting better at it, okay? But it's still research, and figuring out how to get all these components to talk to one another is totally non-trivial. Yeah. Yeah, so are you asking? Yeah, so the little nanoscopic domains, the magnets, we build those using e-beam lithography. That's not available in all clean rooms. But we are developing a method to use phase plates to allow us to do it with just photolithography. And that is available everywhere. So once we get that process going, everyone will be able to build them in their own clean rooms. It will not be prohibitive. Okay, so that's something that we're working on. You're also welcome to contact us if there's something that is aligned in terms of interest. Then we could try to work together to make things and then, collaborate in that way. Anyway. Good. Other questions? Yeah. Have we made A? Yeah, so the magnetic robots are fairly strong because you can jack up the magnetic field and they'll do their thing. The electronic robots, we had to develop actuators that could be strong. So the platinum actuators that I showed you, they only do surface adsorption, or if you apply a slightly higher voltage, they oxidize the surface, but they only oxidize the upper nanometer of the material. So that's the oomph that you have to bend the actuator. And to get around that, to make something stronger, we had to use a bulk absorber of hydrogen. So that's palladium. So our strong actuators are made half palladium, half titanium. You put a voltage on the palladium, it absorbs hydrogen in bulk. Now the whole thing is absorbing and it has a lot more oomph, so you can make the film thicker and it still bends. And that thing, for a half micron actuator, okay, we can lift a bumblebee. And that's amazing, right? That thing is strong. Okay, why don't I take the rest of the questions offline? And I don't know what we say. Do we meet again tomorrow? We meet again tomorrow at 9. All right, thank you.